think that I can still go on. Yeah. It'll be fine.
I might trip over you guys, but you'll catch me, right? All right. Now people listening to this are going to think this is very weird. Okay. Are there any burning questions right up front, you guys? Anybody that is like really confused about something, really needs an explanation? Or do you, yes?
What are we going to need to know as far as like labeling anatomy?
As far as the whole exam too? It's mainly multiple choice. And there is some labeling, but not as much as the first exam actually. Okay, so I would say go through the problem sets again, and then we had that heart diagram. Think about blood flow through the heart. I would say look over that stuff again, okay? But it's mainly multiple choice. I'd say this time 93% of it is multiple choice, okay? All right, there is about 45 questions. There's a little bit more questions than there were on exam 1, but some of them are a little bit wordy, but the ones on the back end you'll tend to go through pretty quickly, okay? All right, there is a practice exam up. I highly recommend you guys go through the practice exam. If you have any questions over the weekend, I'll try to address those. But the exam will be much like the first exam. The practice exam reflects the types of questions you'll see, okay? Yeah.
Will the answers be posted?
Yeah, I will post them, but probably Sunday morning. I really want you to.
Yeah, I was just wondering if you could check our answers.
Yeah, I think that the tendency is to sometimes not do the questions and just look at the answers, and I think that does a disservice because you'll think, oh, I knew that, but then when you actually do it without the answers first, then it's more representative. You kind of look and say, oh yeah, I did get that wrong. You know, so I'll put that up on Sunday, and feel free to email me if I've forgotten to do that. Oh, don't forget to put the answers up. Okay, all right. What else? You guys pretty good with that? Yes.
What equations are we going to know?
Okay, so the equations. Let me just bring that up here. If we go to, oh. Darn. It'll be good to go to the Moodle website. All the answers for the problem sets are up online now, and the practice exam is online. So if we go to okay, I'm just going to go to our site here. Okay, so what did you ask me, Katie?
What equations will we know?
Oh, yep, that's what. I knew I was going somewhere. It's kind of like when you walk into a room and why did I go into this room? Okay, so here's, somebody was asking me about the study sheet. It's this one right here, has all the definitions, and just remember on the back side, this summarizes part 2 of lecture 9, the sympathetic response and how it has effects on cardiac pacing. So just want to make sure you guys know that one. And here's the equation sheet. Not many, but these are the equation sheets that will be on the back of the exam. Okay? Yes?
So I use your lecture outlines. Are you saying that I can completely go over and not look at part 2 and just look at
I hate questions like that because, you know, it makes me anxious. I would say that those two descriptions on these definitions literally do summarize lecture 9, part 2. To be honest, if you knew that, you would be fine for the exam. Okay? Now, remember, this is only one part of it, though. Remember, this is what affects heart rate. The effects on stroke volume is not included there, right? And then increases in heart rate and stroke volume have, like we just did in the other room, and you guys did this morning on the board, has effect on cardiac output, has effect on mean arterial pressure. Your job now is to put all of it together, right? How does it affect the whole organism? Okay? Okay, so let me go back to the equation sheet. This says a lot, right? What did I not give you? I didn't give you how to calculate heart rate using the R to R value, right? How do you calculate heart rate using R to R value? I didn't give you Ohm's law. Mean arterial pressure equals cardiac output times total peripheral resistance. That's good walking around knowledge. Okay, I'm just saying that you should know Ohm's law. Okay, I do give you Poiseuille's law here. That is another version of Ohm's law. Flow is equal to the driving force over resistance, and in this case we have substituted resistance for pi r to the fourth over 8 length times viscosity. So it should be written like this. Q is equal to driving force, and then the pi r to the fourth is actually going to be in the numerator, and then 8L viscosity is in the denominator. So it's kind of written funny, right, on this sheet here, but this is how you could write it on your exam. Okay, this is how it should look. Yes?
Which or all of these do we have to do actual calculations with?
Okay, so you will have to do actual calculations with this one, mean arterial pressure. Poiseuille's law, this is more of relationships. Net filtration pressure, you will have to do a calculation. So, like the practice exam, I'm not ruining anything, right? You're going to have to figure out how to calculate heart rate, right? You guys know how to do that. The practice exam just gives you heart rate, but you guys know how to calculate heart rate using the R to R value. Anybody confused about that? You want me to go through that again? Remember, that is just one beat. You have a P, QRS, and T wave. P, QRS, and T wave, right? The R to R value is these peaks right here, R to R value. The one on your essential calculation, cardiovascular calculation sheet was 800 milliseconds, which is really 0.8 seconds, right? This, if you were going to calculate heart rate, would actually be heart rate equals 1 beat is 0.8 seconds, right? And you would have to convert that to minutes. What you would do is you would just say this is 60 seconds per 1 minute. So you would essentially just say 60 divided by 0.8 is going to give you beats per minute, heart rate. I think that we've already calculated that. Is it 75 or 72? 75? Yep, 75 beats per minute. Okay, so you know how to calculate heart rate. You should be able to calculate stroke volume. Anybody know how to calculate stroke volume? Just right off the top of your head. You can do it a couple of different ways. You could calculate it by subtracting end diastolic volume with the end systolic volume, right? EDV minus ESV, right? That's stroke volume. Or you can calculate it by ejection fraction, right? If I give you the ejection fraction, you should be able to multiply 60% times the end diastolic volume. That would also give you stroke volume, right? Does that make sense? So if the end diastolic volume is a certain amount, what's a good amount? What's a good amount for that? Stroke volume mils per beat. Let's just say it's 140 mils, right? That's a good amount. Yeah, so, and I say that the ejection fraction is 60%. Instead of, if it was 50%, then the stroke volume would be 70, right? Let's just say it's 60%. You should be able to calculate stroke volume from that number. Remember, end diastolic volume is the amount of blood in the ventricle when it is completely relaxed. In the left ventricle when it's completely relaxed. So ejection fraction is going to be that fraction of blood that's propelled out of the ventricle. Right? Okay, so you should be able to calculate heart rate and stroke volume. With that, you can calculate cardiac output. That's not even on your equation sheet. Cardiac output is heart rate times stroke volume. Yes?
So for defining the stroke volume, then you would do the ejection fraction times the end diastolic.
Yeah. Yep. Exactly. So to calculate stroke volume, it's ejection fraction times the end diastolic volume. Times, yeah. So 60% would be 0.6. Okay, so then with that, you should be able to calculate mean arterial pressure. Remember, this equation is given to you. So you would calculate this by knowing the systolic over the diastolic. Right? We've talked about that. Normally, it should be around 120 millimeters of mercury over 80. If you knew those numbers, you could calculate mean arterial pressure at rest. That's one thing I didn't say here. You use the 1/3 term when the body is at rest. If you were exercising, you would bump that up to 1/2. I won't do that to you on exam, though. But just remember that in the future. This would be always at rest. What is mean arterial pressure at rest? Then, if you know cardiac output and mean arterial pressure, you should be able to calculate total peripheral resistance. And you don't have to do any conversion. It's usually going to be millimeters of mercury over liters per second. TPR you would have to calculate, right? So you would calculate TPR by, let's just write that down, mean arterial pressure, this is Ohm's law, is equal to cardiac output times total peripheral resistance. So to calculate total peripheral resistance, you would have to calculate mean arterial pressure, you would have to calculate heart rate and stroke volume, and then calculate cardiac output. And then just by dividing mean arterial pressure with cardiac output, you could calculate total peripheral resistance. Okay? So the mathematics is pretty trivial, but it really does give you a good idea of how, right, blood flow, pressure differences, flow, and resistance are occurring in your body. It is key to a lot of physiological processes. Okay? Yep. So yeah. Go ahead and take a look at. Can you take a look at the screen there? So mean arterial pressure. What's that? That'll be on the. This sheet right here will be on the back of your exam.
But there's no equation for arterial pressure that stroke volume.
Yeah. No. Stroke volume is going to be a variable that's important to calculate cardiac output. Yeah. So cardiac output is heart rate times stroke volume. I'm going to write that on the board too. Cardiac output is heart rate times stroke volume, and that isn't on the sheet. So it is important to know how to calculate cardiac output. Okay? You do have to memorize that cardiac output is heart rate times stroke volume. I have a friend that is an employee at Medtronic, and she swears that in her interview, they started mentioning cardiac output, and she blurted out, oh, cardiac output equals heart rate times stroke volume, and she swears that's how she got her job. I'm not kidding. So So just remember that. That's good walking around knowledge. All right. So any other questions about calculations? You guys pretty good with that? And then net filtration pressure, but this is actually given to you. So let me just, okay, let's just go through these two equations really quickly. If I were to ask you about resistance, what would you have to do to this equation to answer that question? What is resistance equal to? What is resistance equal to with this equation? Yes. Yeah. So just remember you have to flip those variables. 8ln is equal to pi r to the 4th. Then you can answer questions relating to resistance. It is just flip those two variables, 8L viscosity over pi r to the 4th. Okay? So now you can answer questions about how these variables relate to resistance. But you would use this equation to talk about how these variables relate to flow. Okay? Right? Did I confuse you guys, or you're pretty good? Pretty good? Net filtration pressure, just a review from today. If it's a positive number, what's going to happen? It's going to push the fluid out. That's called filtration. If it's a negative number, it's going to pull fluid in. That's called absorption. Okay, so remember those terms as well, too, filtration and absorption. All right, do you guys want to, is there any other questions right away that you're really confused about? Okay, should we just go through some of lecture 7, then some of the relationships? Yeah, let's go through lecture 7. I think right now that is one of the biggest concerns. There's a lot of information, and I'm just going to draw on the board. Sorry, people at home. I'll put the, let's see here. I'm going to go ahead and put up lecture 7, just so they know what we're talking about here. Okay, and let's go with, I thought I had a more recent one, but, okay. I'm going to start right here. Right? We'll start right here at the neuromuscular junction. Are you guys okay with this? Eraser. Is it easier for me to draw on the board, or do you want to look at the screen? Draw on the board? Okay, I think it's easier for me to draw on the board, and then people at home can look on the screen. But, okay, so what we have is the neuron. This is the motor neuron, remember? Whoa! It's weird. That was very dramatic. Wow. Okay. Okay, and then you actually have the muscle cell. Okay? And this is actually called the end plate of the muscle cell. The end plate. This is the motor end plate. Okay? So what happens is those action potentials are propagated down the axon, and it arrives at the axon terminal end, correct? What that does is it stimulates those voltage-gated calcium channels. Remember, these are voltage-gated calcium channels at the axon terminal end. I wrote this as CAV. CAV. CA for calcium, V for voltage-gated. Okay, CAV channels. Now, remember the equilibrium potential for calcium is very depolarized, and there's a very high concentration of calcium outside compared to inside. So calcium is going to flood into that axon terminal end. Calcium is going to flood into the axon terminal. terminal end. Now, in cell biology, if you guys are going to go on and take cell biology, there's a cascade of events that we're skipping right now, right? Calcium binds to synaptotagmin, and there's V snares and T snares and all kinds of docking proteins. We're totally skipping that, okay? So what happens is calcium, there's a chain of events that occurs that promotes vesicle fusion. And those vesicles have a number of acetylcholine molecules inside. So, calcium promotes vesicle fusion. Each one of these vesicles has a very specific amount of acetylcholine. That's what I was talking about with the quantal nature, right? If you just released one vesicle, one packet of acetylcholine, it would depolarize the muscle 0.4 millivolts. Those are called MEPPs, or mini end plate potentials. But what happens with a full-blown, right, activation of this neuron and calcium usually tends to just release a whole bunch of packets into the synaptic cleft. All of this acetylcholine is delivered into the synaptic cleft. Okay? And so now we have acetylcholine in the synaptic cleft. It binds to a ligand-gated channel called the nicotinic acetylcholine receptor. Okay, so that's a name that you should remember specifically for skeletal muscle. Nicotinic acetylcholine receptors. These are ligand-gated receptors, and it actually is an ion channel. This is a receptor that's ionotropic. You guys remember that term. It's an ion channel that allows for sodium to flood in and potassium to move out. So it's non-selective cation channel. Now, we talked about this in class. The question was asked, isn't that an electroneutral like event? How is it that you get anything that occurs when that happens? Remember the chord conductance equation. It actually changes the conductances. So now we're 50% sodium, 50% potassium. It moves the membrane voltage towards zero. If you guys remember that. It does depolarize the cell. So when acetylcholine binds to the nicotinic acetylcholine receptor, it opens up this non-selective cation channel and depolarizes the cell to about 0 millivolts. That's enough of a depolarization, right? These are graded potentials. Graded potentials decay with distance. That depolarization wave propagates in all directions along the end plate. Okay, remember it's a graded potential propagating in all directions along that end plate. End plate potentials are graded potentials, so they decay with distance. And everything you know about graded potentials applies here. Ligand gated, right? Decays with distance. You don't need any summation. There's not any other motor neurons in the vicinity, so you can't get spatial summation. And you only just need one wave, action potentials propagating in the calcium event and the release of acetylcholine. So you don't need to increase the frequency. Just one shot basically allows for these graded potentials to activate voltage-gated sodium channels outside the end plate. Okay? So no need for summation. Don't need to achieve tetanus. It's enough of a depolarization that it can then activate action potentials outside the end plate. Now, this is an excitable cell, just like neurons. Okay, so you get action potentials now that run along, I'm going to use this by its real name, not plasma membrane, but sarcolemma, right? Action potentials move along the sarcolemma and then down the T tubules, right? The T-tubules are just an extension of the sarcolemma. You guys with me? Those action potentials are now propagating down the T-tubule. Okay, so I'm going to move to a different slide here so that we can catch up. Okay, so we're going to move to this slide. So here's where we're at. You can actually see on the slide, action potentials are propagating down the T-tubules and until they get to a voltage-gated calcium channel called the dihydropyridine receptor. This is a voltage-gated calcium channel. It's sensitive to the drug dihydropyridine. That's why it's called the dihydropyridine receptor. But it really is a voltage-gated calcium channel. Yes?
Do you know that name?
You do not have to know that name. I mean, on the exam, but you need to recognize it, right? You don't need to write it out, but on the exam, you'll see dihydropyridine receptors. You should know where that is in the muscle. But it's not going to be a short answer where you're going to have to memorize that name. One thing you should know, I did get a couple of questions about this. This is a voltage sensor. This is a voltage-gated calcium channel. So it senses the voltage change propagating down the T-tubules. However, in skeletal muscle, it doesn't conduct calcium. Calcium doesn't flow through this receptor. It's mechanically coupled to ryanodine receptors that are expressed on the sarcoplasmic reticulum. So this is the voltage sensor. It senses the voltage change. There's a conformational change of the dihydropyridine receptor that translates to a conformational change of the ryanodine receptor. When that happens, the ryanodine receptor opens up and calcium floods into, I'm going to use the correct term here, not the cytoplasm, but the sarcoplasm. Okay? So calcium floods from the sarcoplasmic reticulum into the sarcoplasm. With skeletal muscle, 95% of the calcium that enters into the sarcoplasm is from internal stores, from the sarcoplasmic reticulum. Okay? All right, so what happens next, right? Okay, dihydropyridine receptor is mechanically coupled to the ryanodine receptor. Now, this is a specific subtype in skeletal muscle called RYR1. You don't need to know that, but in the heart, it's RYR2. And there is some major differences between the two. In skeletal muscle like this, it's mechanically coupled. But in the heart, this dihydropyridine receptor actually conducts calcium, so calcium flows from this extracellular space into the sarcoplasm, and then it's the increase in calcium that opens up these ryanodine receptors in the heart. So this is a calcium-induced calcium release. And you can see that this would be a profound positive feedback mechanism. The more calcium that enters in from the extracellular space, the more ryanodine receptors that are going to be activated, the more calcium that floods out of the sarcoplasmic reticulum and activates more ryanodine receptors. Okay, so simply, let me just make this simple in case you're tuning out, because there's a lot of information. In skeletal muscle, it's a mechanical coupling. In cardiac, it's calcium-induced calcium release. Okay, so that's a really important distinction between the two types of muscle. All right, so now calcium floods into the sarcoplasm. This is important. Which protein does calcium actually bind to? What protein does calcium actually bind to? Troponin, which subunit? Troponin C. C for calcium. So troponin C actually binds to calcium. Let's go to this next one. Okay, so here's our troponin C. These are our little red dots here of calcium. calcium binds to troponin C. It causes a conformational change of all three of the different types of troponin, troponin C, I, and T. And you don't need to know that for the exam. But what is the protein that is ultimately moved so that crossbridge cycling can occur? What's that? What is the protein that, it's this long filamentous protein right here that is actually moved to reveal the myosin binding site on actin? What is this protein called? Tropomyosin. Okay? So it's actually tropomyosin, when calcium is not around, that's blocking the actin and myosin binding site. I should say that another way. It is wrapped around actin, and it is blocking the myosin binding site on actin. So troponin C causes a conformational change of all three of those troponin proteins, troponin C, I, and T, and that ultimately moves tropomyosin out of the way to reveal the actin and myosin binding sites. All right, when that occurs, this is another way to look at it. Now you get cross-bridge interaction, right? Now that myosin head can actually bind to that actin. This is the myosin binding site, this black dot there. And cross-bridge cycling can occur. Cross-bridge cycling can occur. Let's go to, oh, this is a nice one. Here we go. Troponin C, troponin I, troponin T. Calcium binds to troponin C, causes a conformational change of all three of these molecules, ultimately moving tropomyosin out of the way and revealing the myosin binding site on this actin filament. Okay, so now cross-bridge cycling can occur. This is important to know. There's a couple of questions on cross-bridge cycling. Essentially what's happening is when calcium rises in the intracellular space or the sarcoplasm, you can see that ATP has already been hydrolyzed to ADP and the inorganic phosphate. They're both bound to the myosin head here. Okay? So the bridge has already been energized. That's the main thing. The bridge has already been energized. Now, when ADP and pi actually dissociate from the myosin head, like this is a 90-degree angle, that's what's responsible for the power stroke, right? It actually moves the myosin head from a 90-degree angle almost to a 45-degree angle, and it literally moves that actin filament, moving the Z discs closer and closer together. Okay, so the dissociation of ADP and the inorganic phosphate are responsible for the power stroke. Okay, the power stroke. Then ATP is required. It has to bind to the myosin head for the actin and myosin to actually dissociate from each other. Okay? Then the ATP is hydrolyzed back to ADP and pi, and that re-energizes the bridge. So now it goes from 45 degrees to 90 degrees, and the cycle can start all over again. Okay? Now remember, rigor mortis is a condition after death when all the ATP leaks out of the cell and it's just not around. Okay? So when all that ATP floods out of the cell, then actin and myosin can't dissociate, and the body is left in a persistent contractile state called rigor mortis. Okay? You guys pretty good with that? Are you okay with rigor mortis? It's Halloween, you know, right? That was a funny question. All right. Okay, so Remember, the myosin heads are walking along the actin filaments in opposite directions. So as they pull the actin filaments towards each other, you actually pull the Z lines closer and closer together. The Z lines, remember the sarcomere is defined from Z line to Z line, or Z disc to Z disc, okay? So that is the single unit of contraction called the sarcomere. That's why you have striations in both skeletal muscle and in cardiac muscle. Not in smooth muscle, though. There's no striations in smooth muscle because they're not organized in sarcomeres. Okay, so what happens with contraction, take a look at this slide. What happens to the A band? What happens to the A band with contraction? Don't turn the page yet. Does it get smaller? Does it get larger? Or does it stay the same? It stays the same, right? The distance between one myosin head and the other myosin head stays exactly the same. So the A band always remains unchanged with contraction. But the I band, you can see the I band, remember, is if you did a cross section, all you would get would be actin, or the thin filaments. The I band is going to diminish, and the H zone is going to diminish, right? H zone is where if you actually did cross section, you'd only get myosin, or thick filaments. But the A band stays unchanged. So let me just go to the next one, because this will be, right? A band stays unchanged. I band is reduced. H zone is reduced. Yeah?
Will the H zone ever just disappear?
It can, yeah, yeah. You're just kind of looking at crude measurements with imaging, yeah. Okay, that's another thing that's really important with skeletal muscle. Once you get stimulation of that motor unit, that motor neuron, the skeletal muscle is going to shorten to its shortest possible distance. It's an all or nothing effect. Okay, that's not the case with cardiac muscle. Cardiac muscle, it depends on how much calcium is released into the intracellular space, into the sarcoplasm. The more calcium, the more forceful the contraction, right? For heart muscles, the more calcium that's released into the sarcoplasm, the more forceful the contraction. The greater the contractility, the greater the stroke volume. Does that make sense? Putting it all together. The greater the contractility, the greater the stroke volume, the greater the cardiac output. Okay, so that's basically lecture 7, you guys. What about those relationships, right? I just want you guys to realize that lecture 8 is online. That's the only one for this one that's online. So if you are really having some troubles with these different relationships, I'm talking the intensity force relationship, the frequency force, the length tension relationship, and the load velocity. There's 4 of them that you need to know. They are online. You can just flip to that one particular slide and listen to the lecture again. Okay. So this is what we're talking about with skeletal muscle dynamics. Before we finish up with lecture 7, how does the muscle relax? How does the muscle relax? There's a couple of different events, right? The circa pump takes over, right? The calcium ATPase, it pumps calcium back into the SR, lowering the amount of calcium in the sarcoplasm. When you lower that intracellular calcium, right, it dissociates from the troponin C. Tropomyosin moves back in front of the myosin binding site on actin, and the muscle slides back to its original position. Okay, so that's how relaxation occurs. Okay, so let's go ahead and move on to lecture 8 here. Okay. Any questions, you guys? Now remember that worksheet. Do you guys remember your the worksheet that you did where you had to put all that in order? That's a really good just summary of the entire lecture 7. So if I were to help you guys just in your efforts to study, that muscle worksheet is just one great resource to compile everything that's going on with lecture 7. Okay? Okay, so lecture 8 starts off with the difference between isometric and isotonic contraction. I actually did have someone in my office today trying to clarify isometric and isotonic, okay? So remember isometric, iso meaning same, metric meaning distance. This is the type of contraction where you're not allowing the muscle to shorten. If I walk off to this wall and I start pressing on it, I'm not moving, I'm not shortening the muscle. I'm not moving bone, but I am generating force. If I had, again, a force transducer on the other side of this ball, I could measure the increase in force as I push harder and harder on this wall. That's an isometric contraction. Now, another way to think about this is take a look at this graph. Anytime you see a graph where the y-axis is tension or force, you can automatically assume that this is an isometric contraction, okay? So if the y-axis is a unit of tension or force, you can automatically assume this is an isometric contraction. However, if we're actually, let's see, if the y-axis, I'll have to go to the load-velocity relationship to find that. Here it is. If the y-axis is actually the distance of shortening, or shortening distance, then you can automatically assume this is an isotonic contraction. So with an isotonic contraction, tonic meaning strength, or same afterload. So when you're picking up a 10-pound weight, you're allowing the muscle to shorten, you're actually moving the bone, but the weight, the strength, right, that's what the tonic is referring to, the weight stays the same. You're moving the bone against a constant weight, a constant afterload. Okay, so that's what isotonic is, but you're allowing the muscle to shorten, you're moving bone. This is basically what strength training is all about. Okay, so let's go back to these relationships. Intensity force was the first relationship. And it was described by using just this upper panel up here. You can just put like maybe an equal sign. This is the intensity-force relationship. Intensity-force relationship, just the upper panel. So in this case, you're only looking at a single twitch, and you're looking at how much force can be generated with a single twitch. So you've got a muscle, a whole muscle. It's in this apparatus that's being bathed with media, nutrients, oxygen, right amount of carbon dioxide, and you have a stimulator that's going to pass a current and shock this particular muscle. Okay, what you'll notice is if you just give it a little bit of a shock, you're only going to recruit a few muscle fibers in that whole muscle, and that's going to generate a little bit of force, but then you're going to allow it to relax back to its original position. That's a single twitch. But as you give it a greater shock, what you're doing is you're passing more current. You're recruiting more and more muscle fibers in that whole muscle until you reach a maximum stimulation, right? At this point, you can't, even if you increase the stimulation more, You can't recruit any more muscle fibers. You've actually recruited all of the muscle fibers in that whole muscle at that particular point. So you've determined the maximum stimulation intensity. Okay, so that's intensity force. The molecular explanation is that you're recruiting more and more muscle fibers in that whole muscle. Okay, so now let's go to the frequency force relationship. There is one tricky question on the exam, and it gets to the heart of the frequency force relationship. So try to really listen to this explanation of the frequency force, okay? It's just a little heads up. And a lot of people get this wrong. So I just really want you to pay attention to what's happening with the frequency force relationship. Now, with the intensity force relationship that we've already determined in this upper panel, we're using a maximum stimulation intensity, right? We're bringing it down to the second panel. So we're using a maximum stimulus intensity, but now we're increasing the frequency, right? Instead of just a single twitch, now we're stimulating it, one right after the other until we can achieve summation. And then if we keep doing that, we have this certain frequency, we can achieve summation and tetanus for that particular frequency. This is an unfused tetanus, but we're still maxed out here. Okay? So, why does that happen? Why? Is it about calcium? Right? Is it about calcium? Here is a single, we've shocked it. We gave it an action potential or we passed a current, and we shocked it but allowed it to relax back to its original value. This is a single twitch. It released a certain amount of calcium into the sarcoplasm and generated a certain amount of force. But when we gave it multiple stimulations, we increased the frequency. Take a look at this. We didn't increase the amount of calcium. Sure, we may have increased the duration that it stayed around in the sarcoplasm, but we didn't increase the total amount of calcium in the intracellular space. But we were still able to generate a whole lot more force by achieving summation and tetanus. So it's not about calcium. It's all about these elastic elements. So with each subsequent stimulation, remember with a maximum stimulation intensity, with each stimulation, we made these elastic elements more and more tight, right? At first, they acted as a buffer, like a shock absorber. But then with each subsequent stimulation, we basically stretched out these elastic elements until the very end with tetanus, when we stimulated the muscle, all of the force was expressed at the end of the muscle, and we could measure a tremendous amount of force compared to a single twitch. So it's about stretching out those elastic elements. The frequency, and this is what happens when you basically have a cramp in your leg, right? You are generating a lot of force, and it can be very painful, which goes along with our severe dehydration exercise that we did this morning too. With the higher viscosity in the blood, you tend to have more fluid, right? Net filtration pressure, more fluid is actually flowing into the vessels to keep mean arterial pressure up. That takes away from a lot of the interstitial fluid in the muscle. And with that, you get an increase in extracellular potassium. And with just a slight stimulation, you can stimulate those muscles to contract, which would cause summation and tetanus and cause cramping. A lot of people, especially in my morning class, were telling me their experiences with severe dehydration, where literally all of their muscles started cramping up and they were in a fetal position. This person told me it was like rocks. All of a sudden their muscles were just like rocks. They just started to feel like rocks. And pretty much passed out on a football field. So yeah, severe dehydration can be pretty dangerous. So that's what's happening here. When you get multiple stimulations, you're going to get cramping. Okay, you're going to get these elastic elements to be tightened up. And now when you stimulate the muscle, all of the force is going to be translated to the ends. They don't act as shock absorbers anymore, and you're going to get a significant amount of force compared to a single twitch. Okay, so this is basically what the muscle is capable of. Now there's animations that you guys can watch, and I can open up those top hat questions too, so you can refer to this over the weekend. Okay, length-tension relationship. This is the idea of preload. Okay, so with preload, the preload is anything that sets the length of the muscle. And I would write that down. That's a really important concept. Preload is anything that sets the length of the muscle. So if we have a lightweight or a very heavy weight, a lightweight might keep the muscle at a very short length, whereas a heavy weight might really stretch out the muscle beyond optimal length. But in any case, that weight would be acting as the preload because it would be setting the length of the muscle. In the heart, preload is the amount of blood that's forced into the ventricle, the left ventricle. The more blood that's forced into the left ventricle, the more it stretches beyond or stretches towards LO. So it's the amount of blood that's forced into the ventricle that's setting the length of the muscle. That's the preload in the heart. So you have an optimal length. This is actually a really nice diagram. At optimal length, you have the optimal number of cross bridges, the optimal number of actin and myosin that can actually interact with each other and generate force. When it's too short, you can actually see that the actin overlaps, diminishing the ability for myosin to bind to it. Also, there's nowhere to slide, right? There's nowhere to go. It's so close already to the Z discs, there's nowhere to go, and so you can't generate a whole lot of force. If the muscle is stretched out too far, you can actually see it slides past the actin filaments, and again, it's diminishing the number of actin and myosin interactions so that it diminishes the amount of force that can be generated when you stimulate the muscle. So that is the length-tension relationship. Luckily for us, our muscles are attached to our bone at basically LO. But in the heart, at rest, it basically the amount of blood that is forced back into the ventricle, the muscle is still shorter than LO, okay? And when you force more blood into it, say when you start exercising, you actually stretch that muscle towards LO so that you can get a more forceful contraction to compensate for that extra amount of blood, okay? So in the heart, it's just a little bit different. It's at rest, set at shorter than optimal length. Yes?
And LO is
Yep.
optimal length?
Yep. LO is actually optimal length. I've had questions like, what is L0? But it's actually LO. That means optimal length. Yep. Don't forget about these elastic elements. In this experiment, what I just explained were basically this red line here, which is only talking about the contractile elements, the actin and myosin. Remember, there's elastic elements at play here too. When you stretch that muscle out too far, it's like a rubber band. There is a recoil effect. Just like the frequency force, when you stretch out those elastic elements, now when you stimulate the muscle, you don't have any shock absorbers so that you can actually measure a greater amount of force as a result. So the passive tension here is referring to the elastic elements. The active tension is the contractile elements, the actin and myosin. And when you add these together, what you observe is the black line. That's just the red line and the blue line added together. Okay? All right, so that's the length tension. All three of those are what you can measure with an isometric contraction. The last one, the load velocity, this load velocity relationship refers to an isotonic contraction. So in this case, you know it's an isotonic contraction because the y-axis, what you're measuring, is distance shortened. And what you're doing is you're oh man, it's getting late, varying, that doesn't even sound right. I can't even think of another word for that. You're varying the weight. Just ignore me right now. You're changing up the weights on the end of this muscle. And what you're getting is you're putting on a light load, an intermediate load, and a heavy load. So let me just show you what you're looking at. Actually, there's a nice animation on that. You're varying the weight at the end of this muscle. You're putting a heavy load, a light load, and an intermediate load, and then you're measuring contraction and how long it takes for the muscle to start picking up that weight, and then you're measuring the distance shortened. How far does that muscle actually shorten, and then put that weight back down? With a light load, obviously it's picking up that weight to about 3.5 millimeters. With an intermediate load, only about 1.75, and with a heavy load, it can only shorten about 0.5 millimeters. Now, the thing that's really important here is the velocity of shortening. The velocity is going to be distance over time, so it's basically going to be this slope. Okay? So if you take the slope of each one of these lines and you plot it, this is what you're doing here. You're increasing the afterload. By the way, the afterload is what the muscle has to work against. The afterload is the weight that the muscle has to work against. So in this case, you're actually working against that weight that you've attached to the end of that muscle, and you're trying to pick it up. With a light load, this green dot is symbolizing this slope of the light load. So you have a certain velocity with the light load, certain velocity, which is this slope right here of the orange line, is right here. And then with the heavy load, see, you're increasing the afterload until you get to this point, and you can see the slope is really a lot more shallow, and this is where you would plot that with the heavy load. When the load, the afterload, or that weight is so heavy that now the muscle can't even shorten, what would that be? That'd be an isometric contraction. Now the weight is so heavy, the muscle is not allowed to shorten. So this would be the isometric, the maximum isometric afterload. And then if you even go further with it and you attach a really heavy weight, you're going to start lengthening that muscle. Okay. I wouldn't spend too much time on this slide, but I do need you guys to know what preload is and what afterload is. The whole idea of this slide was to really introduce the idea of preload. This is the weight that's setting the length of the muscle. And afterload, when you actually stimulate this muscle to contract, it's going to need to work against this weight. This is the weight that this muscle has to work against when it tries to contract and pick up this afterload. In the heart, preload, again, is the amount of blood that's forced into the ventricle, and the afterload is the resistance in the whole systemic system, the total peripheral resistance. The higher the resistance, the higher the blood pressure, the harder the heart has to work, right? That's the afterload, is the high blood pressure. Okay. All right, so going on with lecture 8, This is basically giving you an idea of how ATP is generated, which is important with fatigue. If you are aerobically fit, you're going to stay in this oxidative phosphorylation pathway. Your heart's going to be able to pump enough oxygen to your tissue, and basically you're going to stay in that oxidative phosphorylation pathway and generate a lot of ATP. If you're not aerobically fit, you're going to switch over to the anaerobic pathway, start to build up lactic acid. Your muscles are going to start to burn, right? And at this point, you can't generate a whole lot of ATP, so your muscles are going to start to fatigue. We also talked about creatine phosphate. There's an enzyme that can convert creatine phosphate to creatine and actually phosphorylate ADP. But this only works in the first few seconds of any intense workout. Okay? So there's 3 ways to generate ATP in the cell, and ATP depletion plays a huge role in fatigue. Okay? So that's when you can actually see here you've increased the frequency. So we've reached tetanus, and after a while, the muscle's actually going to start to fatigue. Another important concept is basically the difference between slow oxidative and fast glycolytic. Slow oxidative, let's go to, this is one of my favorite slides here, this one right here. In any whole muscle, you have all 3 types. You actually have the slow oxidative here in red, the fast glycolytic in yellow, and the intermediate type, the fast oxidative glycolytic in orange here. But just by looking at this slide, it gives you a lot of information. The slow oxidative muscle fibers, the ones in red here, they're red because they have a lot of myoglobin associated with them. They have a lot of mitochondria. They're rich with blood supply. These black dots are all vessels bringing blood to this area. And you can see it's pretty much surrounding these red cells, the slow oxidative muscle fibers. So they don't fatigue very easily because they don't run out of oxygen. They have lots of myoglobin that has oxygen. That's a nice oxygen store. They have lots of mitochondria, so they can generate a lot of ATP. And they have a rich blood supply to bring oxygenated blood from the heart. Now, the fast glycolytic, these are the yellow ones. You can see they don't have a lot of myoglobin. They're not red. They're the white meat. So again, no myoglobin, not a lot of mitochondria, no blood supply. They're very powerful because they have myofibrils. They have a greater amount of myofibrils in parallel, so they're very powerful muscles, but they fatigue very easily. So going back to this slide here, you can actually see slow oxidative muscle types at the top here, they don't fatigue readily, even with titanic stimulation, not Titanic. Titanic. The fast glycolytic muscles, they're very powerful, but they fatigue fairly quickly with titanic stimulation. All right. So know the difference. This is a nice table. Take a look at this over the weekend. You can just kind of go through it. There's a few, like 1 or 2 questions referring to that. So this is a good slide as well. What are some of the factors that determine muscle tension? When you're talking about tension or force developed by each muscle fiber, you have to remember the action potential frequency. This is directly related to the frequency-force relationship. You have to think about the fiber length, right? If you're at optimal length, you'll be able to generate the most force. Fiber diameter actually refers to like fast glycolytic The more myofibrils in parallel, the greater the fiber diameter, the more force that can be generated, and where it is with fatigue. So these are all some really good things to think about when you're thinking about what factors determine muscle force or muscle tension. Now, when you're talking about the number of active muscle fibers, you have to think about how many fibers per motor unit and how many active motor units there are. And this is directly related to the intensity force relationship. The stronger the shock, the more you recruit motor units, more and more motor units. So just to help you guys out too with your studying, I would say don't worry so much about flexors and extensors. For my students in the lab, this was a really important concept, but in the lecture, don't worry about these slides, okay? They're interesting, don't get me wrong, I like them, but they're not gonna be on your exam. So okay, so pick up here. I do need you to know the difference between smooth muscle, cardiac muscle, and skeletal muscle. There's like 2 or 3 questions that relate to this. What is the difference between smooth muscle, cardiac muscle, and skeletal muscle? So take a look at smooth muscle here. The major things is that they are not organized in sarcomeres. There's no striations. So with that, there's no troponin. There's no tropomyosin. Right? They're not organized that way. They lack sarcomeres. There's no T-tubules. Not a whole lot of, there's not the sarcoplasmic reticulum that you see in the skeletal muscle. Some smooth muscle cells have gap junctions, some don't. The ones that have gap junctions are considered single unit smooth muscle cells. That means they act in coordination with each other. They actually act as one single unit. Because of the gap junctions, you get a coordinated contraction. Those smooth muscle cells that don't have gap junctions are called multi-unit smooth muscle cells. And they contract in all dimensions, kind of like this right here. Here's what they look like relaxed. You still have thick and thin filaments, so there is still actin and myosin, and they walk along each other, but they contract like this. They actually, I would think about it more as these smooth muscle cells are wrapped around vessels like blood vessels and intestines. So when they contract, they constrict, and they reduce the diameter of those vessels. That's another way to think about it. Okay? All right, so this is a big one. Make sure that you know this one, smooth muscle. This is what's different about smooth muscle when you compare it to cardiac and skeletal muscle. All 3 types, remember, rely on an increase in cytosolic or intracellular calcium. All 3 types rely on a rise in intracellular calcium. But for smooth muscle, it actually activates an enzyme called calmodulin, which goes on to activate myosin light chain kinase. And when I say activate, it actually phosphorylates. Phosphorylates and then activates. So it phosphorylates the myosin light chain kinase. That energizes the bridge. You actually get now crossbridge interaction and crossbridge cycling. And when cytosolic calcium is actually reduces in the cytosol, then you actually can't get those interactions. The myosin light chain phosphatase takes over, and it dephosphorylates and relaxes this neck. This is where all the myosin light chains are, and you don't get interactions of myosin and actin anymore. Okay, so I think that this is an example of single unit and multi-unit. But this is probably an important table It really gives you a nice way to summarize all the differences between skeletal muscle, smooth muscle, and cardiac muscle. So take a look at this. All right, so let's go ahead and move on to the heart. So you guys still with me on this? Want to stretch your legs and maybe stand up a little bit? It is a little bit daunting, right? This is a lot of information. Does anybody have some burning questions about muscle? Remember, the Skeletal Muscle Dynamics Lecture 8 is online, so if you need some more information, you can listen to that as well. All right, so let's go ahead and go to Lecture 9. We'll start off with part 1 here. This is just giving you, and I think you guys are pretty good with some of this information. We first just started with Ohm's law, right? You guys know Ohm's law now. Mean arterial pressure equals cardiac output times total peripheral resistance. The 3 main components of any circulatory system is a pump, a tube, and fluid that circulates. I wouldn't worry so much about open and closed circulation. I think I would focus my efforts on this, knowing the anatomy of the heart and the blood flow through the heart. Do you want me to go through this again, or do you guys feel pretty good about it? No? Okay. Anybody want me to go through this again? Okay, you guys are good with it. All right. The anatomy of the wall of the ventricle, the pericardium. The outside of the pericardium is called the parietal pericardium. The visceral pericardium is actually continuous with the epicardium. Now, just remember, the epicardium is where all of the coronary arteries and the nerves run, in the epicardium. And in between these 2 layers, there is pericardial fluid. Sometimes certain viruses can cause damage to the heart by increasing the fluid in between these 2 membranes. Myocardium, this is the muscle fibers. This is the contractile. This is where all the myofibrils and actin and myosin are. This is what causes contraction of the heart. And then the endothelium has a nice little layer of epithelial cells that line it that they do have some active transport properties that modify the fluid inside that chamber. So, know those. Here's some text if you need to know that. Don't worry about blood or the white blood cells. I'm just saying. For my students that have my lab, they did have to do a lot with blood. But you guys don't need to know that for the test. Okay, so we already know how to calculate cardiac output. We know how to calculate mean arterial pressure. Let's start off here. The electrical signaling is really important. Okay, so the things that you're going to need to know is, where does the electrical signal start? It starts in the SA node because of the expression of those funny channels. These funny channels cause an eroding resting membrane potential. It's a constant, it's not a steady resting membrane potential. It's an eroding depolarization that occurs, which allows the heart, these SA nodal cells, to reach threshold all on their own. There's an autorhythmicity, or a spontaneous depolarization. So what I mean by this is really important. This is a term called myogenic. Myogenic. So these cells depolarize all on their own because of the expression of those HCN, or funny channels. Causes an eroding depolarization so that it can reach threshold all by itself. Doesn't need any neurons, doesn't need any hormones. That's the term that's called myogenic. Myo meaning muscle, genic meaning origin. So we start here in the SA node. The electrical signal starts here. It sweeps through the atria. It actually arrives at the atrioventricular node, or what's called the AV node. but the signal, the conduction speed, slows down tremendously in the AV node. It allows for the atria to completely contract and deliver that last bit of blood into the ventricles before the electrical signal sweeps down what's called the bundle of His, that's that little elbow here, and the right and left bundle branches. So it sweeps down the septum, that's the middle part. That's the tissue in between the left and the right ventricle. Sweeps to the apex of the heart, sweeps up the Purkinje fibers, and don't forget about this. Then the electrical signal is transmitted to the ventricular myocytes. So a lot of people forget that last step. It goes from the Purkinje fibers to the ventricular myocytes. So because of the way the electrical signal sweeps through the heart, it actually causes the contraction to start in the apex and then sweep up the walls of the ventricle. So it's an upward sweeping motion that helps propel the blood into the aorta or the pulmonary artery. Okay? Upward sweeping motion. The pacemaker cells of the fish are in the sinus venosus. We did talk about that. But remember, the ones that we're really talking about with mammals is in the SA node of the right atrium. Now, one thing also, the cardiac cells have lots and lots of gap junctions, so that ensures a coordinated contraction because that electrical signal goes from cell to cell to cell through the gap junctions. All right, so here's the next thing you really need to know. Let's talk about the action potentials in each area. The ones that you really have to know is the ones in the SA node. I want you to know the different phases and what channels are responsible for each phase. SA node and the ventricular myocytes. So what these action potentials are is if I took an electrode and I impaled one cell in these two areas, one cell in the SA node, these are the measurements that I could make. These are the action potentials that would be elicited because of the ion channels that are expressed in that one cell. Okay? So anybody remember this one right here? What is responsible for this zero phase in the SA node? What is it? This is one that is a very common mistake. You would have to guess that it should be either sodium or calcium. It's going to pull the membrane voltage closer to the equilibrium potential. So it either has to be sodium or calcium. Which one is it in the SA node? It's calcium. Yes, it is calcium. This is a L-type calcium channel. What about 3? That one's a little bit easier. Potassium. So remember, potassium, the equilibrium potassium is way down here. So when you open up those channels, it's going to pull the membrane voltage closer to the equilibrium potential for potassium. So 3 is due to potassium channels. 4, this eroding depolarization, is due to funny channels. Yep, funny or HCN channels. Those are the funny channels.
And those are both, they allow in
Sodium and potassium. It's a non-selective cation channel, just like the one we talked about with the nicotinic acetylcholine receptors. It allows for both sodium and potassium, but it's enough of a conductance change that it slowly moves the membrane potential closer to 0. Okay, what about the ventricular myocyte? What is 0 due to? This is sodium. Now, 0 is not the same. This is really important. This is not the same between the SA node and the ventricular myocytes. Phase 0 in the SA node is due to calcium, voltage-gated calcium channel. Phase 0 in the ventricular myocyte is due to voltage-gated sodium channels. You do not need to know this for the test, but in skeletal muscle, the voltage-gated sodium channel is NAD 1.1. In the heart, it's 1.5. So you can see there's different subtypes depending on what type of muscle you're talking about. Okay, so in the ventricular myocytes, 0 is due to voltage-gated sodium channel, very sensitive to lidocaine. Anybody know what lidocaine is? These channels are sensitive to lidocaine. So people in arrhythmia, a lot of time EMTs or paramedics will give you lidocaine to prevent arrhythmias. That affects this voltage-gated sodium channel. What about 1? What do you think? Yep, potassium. It's a little bit of a dip because these are very transient potassium channels. 2 is this prolonged depolarization called the plateau phase is due to what? Number 2, calcium. This is really important. It keeps the cell in absolute refractory period for as long as the contraction occurs. This is to prevent submation and tetanus in the heart. You do not want your heart to cramp up. That's why this action potential is so long, almost 200 to 250 milliseconds. 3 is due to potassium, and 4 is actually due to those leak channels. Technically, they're 2-pore channels, but we're calling them potassium leak channels.
They're both leak channels?
What's that?
Both 4s, like the one
Yeah.
on one side but also
Yes. So for the atrium, 4 is also leak channels. But 4 is very different in the SA node. These are due to funny channels, which allow it to have this eroding depolarization. Okay, so that's really important. That takes care of all that. Now, here's the next one. Now, this is something also that I think confuses students. Even some of my older students, seniors that I've talked to, I want you to realize with the ECG, the electrocardiogram, or the EKG, these electrical measurements are not measurements of each individual cell. This is the direction that the electrical signal sweeps through the entire heart. Okay? This is, again, how the electrical signal, the direction that it's going from cell to cell to cell, and the direction as it sweeps through the atrium or sweeps through the ventricles. Okay, so the main thing to realize is the P wave is atrial depolarization. Atrial repolarization is actually masked by the QRS. The QRS is so large that it masks atrial repolarization. The QRS complex is the ventricular depolarization. This is the depolarization wave as it sweeps through the ventricles. And then ventricular repolarization. How long do you think it is between the R and the T? This is a good question. What is the time period between the R and the T, between ventricular depolarization and repolarization? What do you think? What's that? A third of a second. Oh, that's pretty good. Yeah? Yeah. Let's go back to this right here. Shouldn't it correspond with this? Right? Depolarization and repolarization, about 250 milliseconds, right? That should be exactly, this should be coordinated in time, right? It should be about 250 milliseconds between the ventricular depolarization and repolarization. So I could overlay that action potential waveform and it should be the same duration. Okay, ventricular repolarization, it looks like atrial depolarization. I'm just going to do this really quickly. I think you guys remember this graph. I'll just do this on the board. I'm spatially challenged. Oh. Which way am I facing? Now it's upside down, isn't it? No, it's not. Okay. Can we do this? All right. Oh. I'm back. Oh, not back. Let's see here. Yeah, bright. Oh, I can reduce the brightness. Oh, no, that goes up. There. That's pretty good. Woo, all right. Okay, so remember the P wave is atrial depolarization in this direction, right? Depolarization as it sweeps through the cells is propagating in this direction. That's the P wave. Oops. And then it sweeps down the heart, right? And then up the ventricular walls. That is QRS. So QRS is ventricular depolarization. Okay. Now the repolarization pathway is going to follow the exact same depolarization. As the cells repolarize, they're going to be going in the same path, but what you're capturing on the ECG is, for the T wave, repolarization in the opposite direction. That's why the P wave and the T wave look exactly the same, because depolarization in this direction looks like repolarization in the opposite direction. Does that make sense, you guys? But the main thing that's important for the exam, P is atrial depolarization. QRS is ventricular depolarization. And the T wave is ventricular repolarization. Okay? All right. Let's go back to the laptop here. You guys pretty good with all that? We're not going to get into any of the pathophysiology, so you don't... I know we talked about fibrillation. We actually talked about heart attack or blockage of the AV node, how that looks. Don't worry about any of the pathophysiology. I just need you guys to get the basics down. So, we only have about a half an hour left. How do you guys feel? Do you want to tackle 10? You're doing pretty good? All right, so I would say for part 2 of lecture 9, let's just go through this. Part 2 of lecture 9, as I said before, the best way to study for this is go to, let me just show you where it is, definitions to know for exam 2. When you click on that, you actually scroll down, and I hate to do this, but I would say study this for lecture 9, part 2. This really summarizes it all, right? What happens when you increase sympathetic tone? Those sympathetic neurons that are innervating the SA node, go ahead and put SA node here. They're going to release norepinephrine. The SA node is expressing beta-1 adrenergic receptors. This is a GS-coupled receptor that activates a GS pathway, increases cyclic AMP, increases funny channel activity, increases the slope of phase 4, and basically increases heart rate. That's what you need to know that's the end of lecture 9, part 2. And this is the the parasympathetic. The only thing that's different that I didn't really emphasize is the increase in GERK channel activity. Remember the parasympathetic, that beta-gamma subunit? It actually activates a potassium channel called GERK, which hyperpolarizes the cell in the beginning of phase 4. So not only does the decrease in cyclic AMP, because this is a GI-coupled pathway, GI-coupled receptor, decreases cyclic AMP, decreases the funny channel activity, it decreases the slope of phase 4, but it also has effects on GERK, which hyperpolarizes the cell at the beginning of phase 4. So let me go back to this right here. This is the graph that I want to make sure that you guys know what I'm talking about here. Okay, so this is the graph. Okay, so with sympathetic stimulation, you're going to get an increase in cyclic AMP, which is going to increase the activity of the HCN channels. That's going to have an effect on this phase 4 slope. Now you reach threshold faster, and you increase heart rate as a result. The opposite is true with the parasympathetic. There's actually two things going on here. You're activating muscarinic acetylcholine receptors that are GI coupled. You get a decrease in cyclic AMP, which decreases the activity of the funny channel and reduces the slope. Along with activating those GERK channels that hyperpolarize the cell at the beginning of phase 4, both of those now it takes a lot longer for those cells to reach threshold and fire an action potential, so that really slows down the heart rate as a result. So all of that is actually listed in that sheet, that definition. Both of these are what you should study, okay? Does anybody have any questions about that, you guys? Pretty good? All right, so if we go to lecture 10, am I going too fast? Do you guys feel pretty good about that? Okay, all right. At least you know exactly where to find that information. All right, so let's go ahead and go to lecture 10. The first part of lecture 10 is the Wigger's diagram. Do you guys feel pretty good about cardiac cycle and Wigger's diagram? There are a couple of questions related to this. I can go through this real quick. Okay, here's the Wigger's diagram. Right there. The top panel is actually what's happening in the left ventricle with the pressure. These are all pressure changes. The green line is the pressure change in the left ventricle. The purple line, this bright purple line, is the pressure changes in the atrium, the left atrium. And this dark blue line up here is the pressure changes in the aorta. So the top panel are pressure changes on the left side of the heart. The middle panel is blood volume changes. These are the heart sounds in time, and this is the EKG, the electrical signal. So they're all lined up in time with each cardiac cycle. And if you really need some more information, this is giving you information about what's happening at this point in time. The ventricle is relaxed, it's in diastole. Then you get atrial systole, the atrium contracts. Then you have an isovolumetric contraction, right? Isovolumetric contraction means there's no change in blood volume. No blood is being ejected. This is basically an isometric contraction. Then you get ventricular systole and ejection. Then you go back to ventricular diastole. This is an isovolumetric relaxation. And then ventricular diastole, where you get passive filling again. Okay, so let's go ahead and talk about each one of these stages, because this will really help you think about what's happening with the valves, what's happening with the blood. I mean, it's hard to think about this all in time unless you think about it in terms of the Wigger's diagram. So What happens at first with ventricular diastole is the AV valves are open. AV valves are open at this time. You can see the pressure in the ventricle, that green line, is lower than the pressure in the atrium. So there is passive filling because the pressure gradient dictates that the net flow is going to go from the atrium to the ventricle. Okay? Then you get the P wave. The electrical signal sweeps through the atrium, and now the atrium then contracts. Okay? With the contraction, you actually get a little bump right here. You get a little bump in the pressure in the ventricle and a little bump in the pressure in the atrium. Right? That makes sense. Atrium contracts and it increases the pressure in both chambers. Then the QRS wave. QRS. So the electrical signal sweeps through the ventricle, and now the ventricle starts to contract. This is the beginning of systole. Okay? As soon as the pressure in the ventricle up here goes above, exceeds the pressure in the atrium, the AV valves shut. That's the first heart sound, lub. Right? As soon as the pressure in the ventricle gets higher than the pressure in the atrium, that shuts those AV valves, and that's the first heart sound. So the heart sound should come after the QRS, right? Because it's the QRS, and then you start to contract, and then it shuts the AV valves. Now the pressure is rising in the ventricle, but all of the valves are closed. All of the valves are closed. Pressure is rising, but the muscle is not allowed to shorten. This is an isometric contraction. They actually call it an isovolumetric contraction because no blood is being ejected. Iso means same, volume is referring to the blood volume. So at this point, during this contraction, pressure is building, but no blood is being ejected. That's really important. It's not until the pressure in the ventricle goes above, exceeds the pressure in the aorta, do the semilunar valves all open. Both the aortic semilunar and the pulmonary semilunar, both of those open, and now blood is ejected. You can see the blood volume tremendously falls when blood is ejected out of the ventricle. Then you get the T wave, relaxation. Once the pressure in the ventricle falls below the pressure in the aorta, we're up here, that's when you hear the second heart sound. That's when the semilunar valves shut. That's the dub. Lub, dub, lub, dub. So the dub should occur after the T wave. T wave is ventricular repolarization, right? Then the heart starts to relax. When the pressure falls below the pressure in the aorta, that's when you get the semilunar valves shutting. Then you have an isovolumetric relaxation, and it's not until the pressure in the ventricle falls below the pressure in the atrium do the AV valves open again, and now you get passive filling. Okay, so just by looking at this chart, you should be able to kind of think through the cardiac cycle, and now this is going to make a lot more sense, right? This is going to make a lot more sense when you actually walk through 1, 2, 3, 4. You can see with the ventricles in diastole, you're going to get passive filling. Atria are going to contract, right? The valves are still open. And then the QRS wave. And then the ventricle in the beginning of ventricular systole, that's when the AV valves shut. You have an isovolumetric contraction first, and then it's not until the pressure in the ventricle exceeds the pressure in the aorta do the semilunar valves open. And then you get a ventricular diastole, which is a ventricular isovolumetric, and then it's not until the pressure in the ventricle falls below the pressure in the atria do the AV valves open back up and you get passive filling. Okay? So just kind of in your mind, if you could just close your eyes and think through that process of the electrical signal and the contraction that follows. Remember, the valves open and close only by pressure changes, only by changes in pressure in the chambers. Okay, we already know these terms. I do need you guys to know the difference between bradycardia and tachycardia. Bradycardia is the decrease in heart rate. Tachycardia is an increase in heart rate. But you guys know how to do this already. We covered that in the very beginning. Remember, ejection fraction is equal to stroke volume over the end diastolic volume. And you can also calculate ejection fraction using EDV and ESV. So look at this. Stroke volume is equal to EDV minus ESV. End diastolic volume minus the end systolic volume. Okay, now the idea of preload. This is what I've been saying all along. Remember, as you increase the end diastolic volume, what this means is as you go up along the x-axis, you're forcing more and more blood into the ventricle. As you increase that end diastolic volume, you can increase stroke volume, remember, because you're changing the length of the muscle. Right? The amount of blood that you force into the ventricle actually can move the length of the muscle and move it towards optimal length to give you a more forceful contraction to compensate for that extra amount of blood. This is an auto-regulation. This is actually called the Frank-Starling mechanism. It's named after Otto Frank and Ernst Starling. Now, what's very important here is this effect, this mechanism, is due to the length-tension relationship. Right? Makes sense, right? This is preload. The more blood that you force into the ventricle, this is what's setting the length of the muscle so that you can get a more forceful contraction because it's moving the muscle towards LO. The sympathetic nervous system does have effects on the entire curve, right? When you increase sympathetic activity, you actually shift that entire curve upwards because you're actually affecting the amount of calcium that enters into the intracellular space, right? With norepinephrine binding to the beta-adrenergic receptor, you actually have effects on, this is a GS-coupled pathway. You increase the activity of pKa, which has effects on voltage-gated calcium channels, the ryanodine receptors, that allows for more calcium to enter into the intracellular space. It removes the inhibition by phosphorylating phospholambin and increasing the activity of the circuit pump, and it tightens up the elastic elements. The end result here is that you can get a more forceful contraction and increased stroke volume and a faster relaxation compared to normal conditions. Okay? All right. Blood flow then, we talked about arteries. We actually talked about some of the blood velocity. I think the main thing here is to be able to calculate blood velocity. Actually, it's not about running any numbers. It's about knowing the relationships. So, velocity equals flow over area. So as you increase the total surface area like you do in the capillaries, as you increase that area, you decrease velocity. So I'm going to write this on the board here. Right? Here's the relationship. Oops. Velocity equals flow over area. Velocity has units of centimeters, distance over time. You can say seconds or minutes. Flow is centimeters cubed, right? That's mils per minute. I better make these units consistent, so I'll make this one minutes. And area is expressed in centimeters squared. So, right, centimeters cubed and squared, that leaves you with centimeters per unit of time. That's velocity. So as you increase the surface area, total surface area in the capillaries, you decrease the velocity. That's the main thing here. You decrease the velocity. So the speed of the blood slows down tremendously in the vessels to allow enough time for the gas and nutrients to exchange in that area. Allows time for diffusion to occur. Okay, so let me back up here. We've talked about Poiseuille's law already. We talked about arteries being much more elastic, right? Arteries are more elastic than even muscular arteries, arterioles, especially the veins. So there's a recoil effect. Arteries actually act as dampeners. They lower the oscillations, but they also recoil to keep the blood moving even in diastole. I think that's the major take-home message here. So that recoil effect helps to keep the blood moving even during diastole. We learned how to measure blood pressure in the brachial artery, and we learned about these two terms, arterial sclerosis versus atherosclerosis. Remember, arteriosclerosis is just a general term that describes hardening of the artery. That can be due to a number of different conditions. Atherosclerosis is a particular type of arterial sclerosis. Atherosclerosis refers to hardening of the arteries because of cholesterol plaques that form, specifically due to plaque formation in the vessels. Atherosclerosis. Okay, remember that the arterioles are a dynamic site of regulation. There's a lot of smooth muscle cells surrounding these arterioles, so the resistance increases quite a bit in that area. Pressure drops. The main thing here, the regulation, I don't want to go through this too fast, but the main thing here is that there are extrinsic and intrinsic mechanisms at play here that are playing a role in regulating arteriolar diameter and radius. Extrinsic mechanisms include sympathetic tone. It also includes hormones like vasopressin that constrict arterioles, or angiotensin, another one that constricts arterioles. So any kind of external input by neurons or hormones is an external mechanism. Now, this slide is showing you intrinsic mechanisms. The smooth muscle cells also have the capability to sense the metabolic state in that particular area. So whenever there is a decrease in oxygen or an increase in carbon dioxide or waste, it's going to be sensed by that. It's going to be sensed by the smooth muscle cells that surround that vessel, and as a result, it's going to vasodilate to decrease the resistance and increase blood flow in that area. So there's a couple of ways that could happen. One way is that you just start exercising, or there's an increase in metabolic activity of that organ, decreasing the amount of oxygen in that area. Or it could be some kind of circulatory issue where there's already a decrease in pressure, arterial pressure. That will also decrease blood flow to that organ, and the end result is going to be a decrease in oxygen. Either way, no matter what the cause, it's going to be sensed by that smooth muscle cells surrounding the arterioles, And they'll both dilate as a result of the decrease in oxygen and increase in carbon dioxide, which will restore blood flow to that area, bringing in more oxygen and taking away more carbon dioxide. So again, this is myogenic autoregulation, and it's an intrinsic mechanism to control arteriolar diameter. Vasoconstriction will be the result. Okay, and I think this is pretty much what we did today. After we talked about arteriolar regulation, we talked about capillaries. So here's where we kind of ended today. Hopefully you guys remember this lecture. Some of you only had it about an hour ago. So if you guys have any questions, I can stick around for a little bit while. But that was a marathon session, especially for the 3211 students. No. Yeah, I would say concentrate on it. Good job. Now, hopefully I recorded all this. Yeah. Please work.
Thank you.